Okay. So, shall we start? All right. Good morning. Thank you for coming and welcome to another seminar, Institute seminar. Today, it's our big pleasure to introduce Professor Celerino Abad Zapatero, who is coming from University of Illinois, Chicago. Cele Abad Zapatero received his licenciado degree in physics in Spain, and he went to the US with a Fulbright scholarship in 1972 to pursue graduate studies in biophysics, micromolecular crystallography, at the University of Texas at Austin. He obtained his PhD in 1978 and continued to do postdoctoral work with Michael Rosman at Purdue University, where he was a team member of the group that determined the first complete fold and amino acid sequence 3D structure of southern bean mosaic virus. After his postdoctoral work, he did structure-based drug design at Abbott Laboratories for over 22 years, retiring in 2008. After his retirement, he has been doing structure-based drug design at the University of Illinois, Chicago, in a variety of targets, mainly related to tuberculosis therapy. Most recently, the protein homeostasis regulator CLIP-C1, that is an essential target for tuberculosis survival, as an affiliate member to the ITR, Institute for Tuberculosis Research at UIC. The ITR focuses on the exploration of novel natural antibiotic cyclopeptides as solid leads to guide structure-based drug design of novel antibiotics. Additionally, he has been pursuing his strong interest in the use of alternative variables, for example, ligand efficiency indices, to expedite drug discovery at the combination of artificial intelligence and alternative variables in drug design. So, thanks, Fele, for coming. The floor is yours, and let's enjoy.
Thank you very much. It's really a pleasure to be here after so many years. You can see in this photograph from 1983, probably spring, summer, but this is a epoch-making photograph. You can see, I'm sorry if let me see if this works. How come? Oh, I'm sorry. Oh, there we go. You can recognize many of these names and faces, perhaps, but that's myself right there. In 1983, I was at the time in transition between getting some paperwork to go back to the US as an immigration and get residency. I had been in the US at this time, 1983, for over 6 years, and I had to get permission to get back to the US as an immigrant. In any case, I came to the group of Severino García Blanco. I'm sorry. I'm sorry, with the logistic. In any case, I was trying to explain to you that I was here temporarily for a few months while my paperwork to go back to America as an immigrant. I was here and I met these amazing kind of people. At this time, Pepe Fallos, Martin, of course. We had the memories together. We just reminisced a little bit together. And then I should point out that Aurea Perales, at the time, was the only person that was a pioneer in macromolecular crystallography at the time. She had been at Birkbeck College with Tom Blundell, and then that was my point of connection. I had obtained a Becca March to stay here for a few years, for a year or so, while my paperwork got arranged. So I got, we imported, with the help of Martin, the packaged protein from Stegeman to do protein crystallography. We tried to contact with the University of León to grow crystals of the first protein in Spain. We moved things at the time, but it was an heroic effort, I can tell you that. It was very heroic. Nonetheless, it was an amazing group of people. Here's Sagario, and here's, of course, Severino, and other people, here Pepe Fallos, etc., etc. I cannot recall the names, but we reminisce with the help of Martin. We have been able to reminisce and find that. Apparently, you can find all these names in the portal of the website of this institute. You can go there and identify every single person there. In any case, I came to talk to you because I was at the Congress in Budapest talking about the structure-based drug design on tuberculosis targets. And that was my interest. And you've seen the title. So I'm going to be talking about that, but I will take a few parentheses to talk about the basis of crystallography, a very simple way to follow up the concepts. So that's my concept of the seminar. So I'm going to introduce a bit of the environment where this work has been taking place. We are talking about here, these are the molecules I'm going to be talking about. This is the N-terminal domain of a protein called CLIP-C1, and we are going to be talking about the complex of rufamycin with this target. This is a complex of the different peptide, which is called ecumycin. I will describe the details. But in addition, I want to convey to you the magic character of this city of Chicago. You can see that I call it the magic city of, on the back, Ogaish, because this is the edge of Lake Shore, Michigan. Lake Michigan is on the airplane, the American Airlines flight such and such. I was approaching Chicago, and you can see the fog that gives this kind of a mystique and magic state and status to the city of Chicago, in a way. I am associated with the University of Illinois in Chicago, Institute of Tuberculosis Research, and also the Center for Biomolecular Sciences. These are the two initials, and this is my pleasure to be here. So let's talk about the science. I will not convey the concept of the tuberculosis issues. There is tremendous resistance to tuberculosis, and so there is still a drive to produce compounds that are better than the one we have now. Because the current regimes require 6 months of therapy, and they are too expensive, and people don't comply with the regulations until they get back, and tremendous resistance to tuberculosis. So we have been focusing on a target which is called, in the jargon of biochemistry and biology, the CLIP-C1 protein homeostasis system. It's a machinery that exists in many, many organisms that actually is involved in the regulation of the amount of protein that you have synthesized. If a protein is damaged or deteriorated for any reason, that protein is labeled with a target, with the arginine target. So you phosphorylate the arginines, and with that kind of a tag, that those proteins are tagged for degradation. And they enter in the machinery, which is called the CLIP-C1 here. This is the machinery. This is the pepper mill, what I call the pepper mill analogy. You have a cup, you have an entry point. When the proteins are tagged and going there, there's a regulating module, which is called the CLIP-C1, the one I'm going to be talking about, and this actually feeds the proteins after unfolding into the hydrolysis unit. So they go through here, they enter, and in this chamber, they are hydrolyzed. And at the end of this process, the proteins are degraded to amino acid levels. And this is how you regulate and recycle the amino acids in it's a CLIP-C machinery. And you can see here, and very sketchy, you can see the hexamer. This is the CLIP-C1 target I'm going to be talking about. And there is now the hydrolytic unit is called by two different hydrolytic proteins, the CLIP-P2 and CLIP-P1. And there are several targets, and of course, toxins and amino acids, etc., that come through here, but this is going to be the target of our investigation. And as a matter of fact, the entire hexamer is very long. We are going to be talking about the N-terminal domain that contains only 150 amino acids. So this is an atomic rendering with cryo-EM. It's not the same species, it's not the same tuberculosis kind of entity. It's from this satellites in the PDB obtained by cryo-EM, but this is the concept of the quasi-atomic level. This is the quasi-atomic level. This is my kind of analogy on a pepper mill, and these are the parts here. So this is the part we are talking about. This is the hydrolytic machinery, and this is the CLIP-C1 target for our work. Keep that in mind for reference. So our work, not only our work in our laboratory, but also laboratories in South Korea and other laboratories have been working on a campaign to identify compounds which are active against this kind of against tuberculosis based on this concept. Molecules that will inhibit the CLIP-C1 machinery. And there have been, of the order of 60,000 actinomycete cultures. There have been, screened for activity against tuberculosis, and they have identified two compounds that I put here, two cyclopeptides, a kind of a very simple mnemonic. I will discuss this in detail. We are going to be talking about rufamycin, which is a heptapeptide, and ecumycin, which is a tridecamer. So ecumycin and rufamycin, and I will explain this in detail now. But then after this, what they have done is try to isolate spontaneous mutants which are resistant to those compounds. And in that process, you identify the gene and the protein that is responsible for these compounds being bound. We have express the protein, purify the protein, crystallize the protein, and also characterize it by SPR, surface plasmon resonance. I don't know how this is called in your jargon, but this uses reflections on complexes, but mainly, and this is the purpose of the talk, we have been using X-ray crystallography to identify how these compounds bind to the target, why they act, and what they actually result on as to the inhibition of tuberculosis. This is the detail of the peptides. You can see the complexity of chemistry of natural products. This is the cyclomerine that was identified first on some marine species. Cyclomerine will be a reference point, but for the purpose of my work has been rufomycin, which is a molecule which is very similar to this with an additional ring here. Both of them contain an element which is called the epoxide. If there are any chemists in the audience, that's the epoxide group. I'm sure they're familiar with that. Very important, as you will see in a minute. And then we have identified particularly the long one has a very long tail. There is 10 amino acids in this ring. There's a tail, and the closure of the ring is produced by a deoxypeptide, so that the threonine chain here, side chain, makes an ester bond with the carboxy end of the molecule, and it creates a deoxypeptide. And so this is residue number 1, this is residue number 13, and this is the closure. This is 13 amino acids. In the jargon of the British, it's a 13-mer and a 7-mer. These are 2 are 7-mers, and these are 13-mers. There's also compounds that have been used for reference, which are these compounds similar but a shorter tail, a modified tail. It contains the same elements, but does not have the epoxide ring. So this is going to be our actors in this scene. For the sake of giving some biological parameters, we measure the MIC, which is the minimum inhibitory concentration of these compounds. You can see that they are nanomolar compounds. This compound binds to the target, which is our ClipC1, at the level of nanomolar. Very, very potent compound, nanomolar compounds. For this, for the rufomycin, for the ecumycin also, the same order of magnitude. These ones without the tail are weaker. You know that larger is weaker, and that is relevant for the discussion later on. Cyclomerine was the original one. It's still not as good as the other one, and there is another one, lasomycin. But look at the kind of parameters that we measure in vitro to characterize these compounds. We measure the MIC, we measure SPR, etc. And like I said, for the purpose of structure-based drug design and to try to improve these compounds, we do X-ray crystallography, structure-based drug design. These are the references here. Now, the first structure that came up in 2013 was done with cyclomerine, which is, like I mentioned, a 7-mer also, like a rufomycin, but they did the structure, and they were able to find how they bind. This is the actual N-terminal domain. Notice that the enzyme, the protein ClipC1 is a very long polypeptide chain, 548 amino acids, very large. But for reference, this is what we are going to be talking about. The NTD, which is a small fragment here, has also now ATPase domains that bind to the ATP to unfold the proteins. So these proteins are able to provide energy with the ATP, unfold the proteins, and feed it back into the machinery to hydrolyze them. That's how it works. They found resistant mutants that they map in here. For our purposes, they map here, which is the area of resistant mutants to ecumycin, resistant ecumycin sites. These are the resistant rufomycin sites. So how do they bind? How do they bind? And they found in this paper, 2013, they bind this way. So I'm going to make now a parenthesis to describe and present to the audience how this technology works. Crystallography, a little bit of that. Just a little bit, just a taste of it. And this is coming for something that I call the magic encounter between the atoms and the X-rays. The magic encounter between crystals and X-rays. You don't know about this, but you should read about it. It took place in 1914, actually 1912, I'm sorry. 1912 is when the first X-ray diffraction of a crystal was obtained. The famous experiment of Laue, Friedrich, and Nippin that showed for the first time that X-rays were waves that could be diffracted, and crystals had atomic arrays of atoms. Magic encounter, magic experiment in humankind, in my opinion. Nobody recognizes this, but it was a magic encounter. Crystals on one side, X-rays on the other side. So the experiment proved, and you can see here, this is the first hints of a diffraction pattern of copper sulfate. You can see there is discrete spots here, but not very clear. But it was due to the experimental skill of Nippert and King that they were able to produce these gorgeous photographs of the diffraction of zinc blend, sulfur of zinc. You can see this is the preliminary crystals. They were not very well formed. You know that sulfate crystals, copper sulfate crystals, are not very good. But look at the ones for zinc blend. You can see that they discovered the symmetry in the view, for symmetry, and then 3 for view, the magic encounter between X-rays and crystals. 1912. In addition, 1914 is another magic encounter. How can you extract from these patterns the structure of the crystal? Bragg's, the Bragg's, 1914. That is the trick. So 1912 were the first experiments, 1914 was the first interpretation of those diffraction patterns in terms of the structure, the atomic structure of crystals. You can see here, this is of course a model now, and I have drawn here the planes that define these crystals and how Bragg was able, the younger Bragg, was able to interpret this structure as an array of atoms and planes that originated to give the Bragg's law. This is how it came about. They were able to say there's a reflection. See, there will be a reflection of X-rays on the surface of the crystals, and I can find the spacing between this plane and this plane. This is the Bragg law. You go after that, you go into the, the reciprocal lattice and Bragg, etc., and Laue, and etc., etc. But this is the concept that originated, and that was 1914, from here to here. The two Braggs, the father and the son. Now, the culmination of this kind of work in 1914, it was a major, it was the structure of penicillin. Among other ones previous to that, there were minerals, but the first biological molecules, chemical molecules, small entities that had relevance in biology were molecules like, small molecules. In particular, this is penicillin. Now, penicillin was, as you probably know, from Fleming, discovered in 1928. He said that it was this secretion from the fungus penicillin that will kill bacteria, in particular, pathogenic bacteria. Nobody knew what it was. Nobody was able to do anything with it. And in fact, the British team that discovered penicillin and continued that work came to the US to mass produce penicillin before the D-Day in Normandy, 1944. And they were able to downgrade the price of penicillin from $20 a milligram to 50 cents a milligram. And so the doctors in D-Day were loaded with penicillin. And they will sprinkle the penicillin on the wounded soldiers, and they save their lives. Because more people will die of infections after the wounds than for the actual wounds. So it was an important item. Nonetheless, the structure was a secret. And Dorothy Hoskins was only able to publish the structure of penicillin after World War II. They were afraid that if they will discover, the Germans discover what penicillin was, they will make the structure and copy it. But in any case, it was only late I was able to. But look at the beauty of this. Even at the level of 1945, you can see the beauty of the Fourier synthesis. Look at this. The atoms of the. This is a copy. I had a copy from the Oxford Museum of Science. You can see the maps of Dorothy Hoskins. This is a copy of it. Look at the maps. Sulfur, the most electron-dense atom. Here it is. It's an amazing discovery, an amazing interpretation of these maps by Dorothy Hoskins, who interpreted many other maps. But this is a climax of crystallography at the time, 1945. The wonder drug. It could cure anything. This is how it worked and how they understood the structure of chemistry. Nobody knew what the structure was. It was a very unstable compound. It was impossible to synthesize. It was mass-produced, the beginning of biotechnology. Biotechnology was not invented now. It was invented in the 30s and 40s. And there's a town in Chicago, in Illinois, called Peoria, where they found the best strain that produced penicillin because there was a lady that would go to the market every day in Peoria, Illinois, to find the best possible rotten fruit. And he will bring that sample to the laboratory, and they found the best strain producing penicillin. Peoria, Illinois. There's a lady called Moldy Lady that will go to the market. In addition to 100,000 sorties all over the world to find the best producing strains of penicillin. But it was next door, in the market in Peoria, Illinois. In any case, I'm going to now present a different thing to impress upon you that diffraction is not only between crystals and X-rays. And that's for everybody. You can tell your neighbors and your son and your daughter and your grandchildren how you can see diffraction in your household right away, right there. I found this December the 8th, 2021. I have seen that before. I couldn't actually understand, but at that time was a magic moment. Watch out. I was in the living room, and I saw these little things poking out through the living room. You can see myself there with the iPhone camera through the window. This is the living room, you know, a table, etc., etc. I watched, and I saw through the window, I saw these little images through the window. I said, what is going on here? I'm looking at the parking lot of the condominium. What do you see? Now, what do you see? You see this, of course, and you see this, and you see this. So now, what is this? Can you close up on it? What is it? Can you close up? It was Christmas, so I can speculate. Was this an UFO? No, probably not enough. This is actually the star that was guiding the Magi to Christus, to Jesus in Bethlehem. What is it? What are we seeing here? So what is this? Now, this is the magic of explanation. Light from the bright, intense lights on the parking lot diffracted, literally diffracted, by the screen grid in front of the glass window. Now, many glass windows in America have the screen shells to protect from the mosquitoes. And you can see that here. It is the grid. See the grid? See, wire grid, right there. So that's what you're seeing there. You see the diffraction pattern of the grid, of the grid because of the lights in the back. Sorry, let me go back for a second. I had to go back. Sorry. I'm sorry. I knew this could happen. Let me just emphasize that again. What you see is that the diffraction occurs not only between crystals and X-rays. So be aware of this, and you will see it, I'm sure, in your household. And you will tell your neighbors. This is what I do every day in the laboratory. This is how I obtain the structure of the atoms in the crystals, because based on these spacings, I can find the spacing of the grid in a vertical direction. Based on this, I can find the spacing on the horizontal direction, etc., etc. So this is the origin. That's what we care. If you measure the diffraction pattern, the intensity of these spots here, you can identify the orientation and the diffraction of these objects in there. So this is why I wanted to take a small parenthesis to introduce upon you the fact that diffraction patterns occur not only between crystals and X-rays, but also when they commensurate of the wavelength of the radiation, commensurate with the size of the object. Then you get diffraction, no matter where you are. So, in conclusion, chance favors only a prepared mind. A very famous quotation from our friend Louis Pasteur, that the doctors will dismiss him as saying, oh, he's just a chemist. He doesn't know anything about these things. In any case, so be aware of all these things and try to identify it. And you write to me. So I found it. In any case, based on that concept, you are going to see here, when you use our new technology, the diffraction pattern by the synchrotron radiation coming from synchrotron of the IPS in Chicago, a very famous, very intense, very intense, see this works? Has the battery run out? Oh no, sorry. This is a very intense, very sensitive detector, ultra-fast detector. You can see the diffraction here, barely in the spots. They are gorgeous crystals, cubic crystals. They appear to be tetragonal, but they're in fact cubic. Rhombidodecahedral. You can see the spots here. So this is the same magic that Bragg and etc. discovered in 1914. The diffraction of X-rays by crystals. We are using new technology, an APS as a source, a synchrotron radiation. But look at the data I collected. I want to emphasize for the people crystallographers. 900 frames, 108 degrees, 0.2 degrees per frame, extremely fine slicing, now 2.4 seconds per frame, collection time 36 minutes, reflections, observations 1,000,000.7, unique 45,000, about 34 redundancy. This is the kind of data you obtain these days with the synchrotrons and the APS and other synchrotrons. And you have the good crystals. Resolution diffraction up to 1.4 Amsor resolution. Like I said, and I will emphasize that right now so you learn something about hardcore crystallography here. Crystals that appear to be tetragonal, at the moment I thought they were actually lysozyme. Say, what is going on here? This is lysozyme. What is going on? Tetragonal, it's P4-1-1. That's it. Well, never mind. So, upon further analysis, this is a good lesson for crystallographers in the audience, I did a small solution, sorry, an identity solution of the crystals in tetragonal form. So tetragonal molecular replacement, remember Michael Rosman, molecular replacement? Michael Rosman, molecular, you try the molecular from the cyclomerine from the PDB and put the Eclipse NTD there, molecular replacement, bingo, I had the solution in minutes. It gave me a solution that was approximately correct, but I was not happy with it. So what happened? I did process the data tetragonal, but I did a rotation function to understand the true symmetry of the crystals. And how do you distinguish that? You look for 3-4 axes. Tetragonal systems don't have 3-4 axes. When you do the rotation function, you find in the rotation function, you find that there's a very prominent peak, chi equal 120 degrees, along the body diagonal. Bingo, cubic. You know right away it's cubic. And then you say, well, it's cubic, and then you just try to do molecular replacement in cubic systems. The structure came out immediately. Gorgeous data, gorgeous symmetry. We found the compound bound, miracle of miracles. But remember, sometimes you may process the data in the wrong space loop, try lower symmetry space loop, try the rotation function, it will give you the exact symmetry of the space loop. Keep that in mind. The lesson for the hardcore people in the audience here. And this is what we saw. Isn't this amazing? When we try the molecule at the first Fourier transform, we saw this. This is the Eclipse NTD domain, unbiased density. Here's the cap, which is actually the rufomycin on top of it. We interpret it, blah, blah, blah. This is the refined structure. You can see this nitrotyrosine, you can see all the elements of the ring, the hexagonal beam. So this is 1.4 resolution, refined, and these are the statistics. Hard work, are free, etc., etc., etc. This is all published. I will talk about this now because I will refer to the chemistry also, as to how this data helps us to produce better compounds for tuberculosis. This was the starting point. Now, this was the different one. This was the ecumycin. This is an amazing story also again because it was a very low symmetry space group, P2 sub 1, and after the structure is solved, I will just, we found also some 3-4 axes of symmetry by the same trick, molecular replacement. Process at low symmetry, try the rotation function, and you will know the exact symmetry of the space group. In any case, here we found P21, we found actually it will be monoclinic, it will be 12 molecules in the asymmetric unit. It will be orthorhombic, it will be less, but nonetheless, we've gone through the symmetry, etc., etc. We found actually solved the structure using P2 sub 1 and 12 molecules in the asymmetric unit of the NTD domain. Now, surprise. When we did that, we found that in fact, there were actually 2 molecules of the ligand per molecule of the target. So it's 1224 of the ligand. So this is the asymmetric unit of that crystal. This is the P2 sub 1 axis. You can see the molecules of the target in the, of course, canonical kind of a cartoon method, and here's the actual ecumycin bound. But like I said, we found there are 2 molecules per target related by 2-4 axis of symmetry, non-crystallographic. Here it is. Actually, here's the 2-4 axis. This is the ecumycin number 1, sign number 1. This is the ecumycin number 2. You can see the peptide here with the tail, etc., etc. This is to give you some hint of the crystallography, how complex it was. This is published in Acta Cris also. So now, how do we go from here as to what is relevant for drug discovery purposes? This is the technology, the crystallography. How do you go from there to design better compounds for tuberculosis? This is the ecumycin structure. You can see how, and I didn't emphasize that before, I could go back, but the fact is that ecumycin has 2 phases. This phase here is hydrophobic, in which all the N-terminal, all the amines, all the amides from the polypeptide chain are methylated. So these are N-acetyl here. So this phase is hydrophobic, but this phase is polar. These amide protons are not sealed, and so this is critical because this actually induces folding of the N-terminal domain of the protein. The 3 amino acid residues here are aligned and make a beta-seed structure. So molecule 1 of ecumycin, molecule 2 of ecumycin, 2-4 axis of symmetry, and here's the actual interaction between the ecumycin tail and the ring with the N-terminal amino acids. You can see them here, MED1, GLU3, Phi5. Here they are. Here they are. and this is actual contact. This is actually the structure of ecumycin by itself, as a small molecule. It's like a little bird with a tail. But this is how they come about together with the two parts of symmetry. And now, this is like I was mentioning, I highlight the parts which are hydrophobic and the parts which are hydrophilic. The hydrophobic circles indicate the hydrophobic parts that produce an interaction across that board here, across the surface. This is the polar side, and this is the apolar side. All right? So now, what happens? What else do we discover here? Well, we discovered something very interesting. Besides the overall fold, etc., we found that in rufomycin, that had an epoxide in the native structure, the ring is open. There's actually a covalent bond between the N-terminal amino acid residue, methionine, sulfur, and the epoxide ring, which is open. So that's another surprise, high resolution. You find that the epoxide actually bound covalently to the N-terminal methionine SI chain, which is unheard of. So this is part of the chemistry. You can see the residues here, the quality of density, as I pointed out, is 1.4 Angstrom resolution. You can see the ring here, this ring here. But that allows us to see that this epoxide was open, and there was a covalent bond between the two. This is the actual binding into the rufomycin pocket. PDB structure is published. And this is what we saw, that actually the rufomycin creates like a beta sheet bridge over the hydrophobic area into the target. Here is the actual hydrophobic ridge, F2, phenylalanine 2, phenylalanine 80, and this is bent over that. You can see here that the ring is open. There's no epoxide here. This is the way it folds over that ridge. This is a hydrophobic ridge, and this is the V over it. And this is the epoxide open. This is the surface rendering. Here's the evidence for the covalent bond between the methionine 1 and the rufomycin. There is density here, not only for our structure, but intriguingly enough, the people who published cyclomerine first missed that. They had the same epoxide, but they missed the covalent bond. They didn't talk about it in the paper. They completely missed it. You have to be astute enough to see. So what you do is you actually mutate the the methionine, make it alanine, do the refinement, and you can see the density connecting the two. No ambiguity whatsoever. Here's the actual chemistry behind it. Here's the epoxide from the tryptophan. Here's the methionine from the N-terminal methionine. It's a necrophilic attack. The ring is open, and you produce this. And that's what you see in the crystal. And here it is. Sarcomania has an epoxide. We don't have an epoxide. These people missed it. It was there, but they missed it. So we went to the PDB and reproduced the same results and actually saw that there was also a covalent bond into that structure. Moreover, we were able to incubate the protein, the N-terminal domain that we're working on with this rufomycin, incubated for 24 hours, and you can see by mass spectroscopy, this is the native CLIPSI NTD. When you add the rufomycin, the molecular weight changes from 70,500 to 80,000. This is the rufomycin structure. So we show that in solution, that also happens by mass spec. You incubate the two together, and you see the displacement of the molecular weight. We had to do it to convince ourselves that it was real. It was not an artifact of the crystals. And this is actually the ecumycin that I mentioned before, that binds in two sites, and they are related by two 4-axis of symmetry, an intradomain 2 4-axis in the CLIPSI NTD domain. This is a duplicated structure. Here's ecumycin 1, ecumycin 2, 2 4-axis of symmetry, and that's what you see. And this is actually mutated residues that we found in the early studies. The mutations happened here, and they were resistant. And again, here emphasize the fact that this tail, between the two copies, there are some small variations in the tail, but the core is the same. Here it is the actual DEPSI peptide. The density for the DEPSI peptide showing that actually the threonine number 10 binds to the threonine number 3 binds to the carboxy end of 10 and creates a linkage. This is the beauty of the surface rendering. You can see here, I can emphasize what we discovered. This is the N-terminal domain of the target. This is the tail of the ecumycin. This is the ring of the ecumycin, molecule 1, molecule 2, the 2 4-axis. This is a hydrophobic area, and this is the tail. And we also did SPR, as I mentioned before, to see that was true also in solution. And when you run SPR, you find the appropriate binding constants and the stoichiometry, and you find that the molecule that we discussed before with little tail and ecomycin have a stoichiometry of 2 versus rufamycin. So it's 1 to 2 for ecomycin, but 1 to 1 for rufamycin. And these are the properties. This is a trace of the SPR studies. The two sites overlap. You can see the two ecomycin 1 and 2. Here's rufamycin. They overlap on this side here, but they occupy a certain part which is common, but certain parts which are different. And moreover, I will devote 5 minutes or less to actually discuss and describe the oligomers that we found for rufamycin versus ecomycin in the crystal. In rufamycin, we found a very compact hexamer with 3-2 symmetry. Here it is. You can see the PISA analysis of the interactions. Very, very low energy combination of particles to create a 3-2 hexamer. This is the top view, 3 and 2 underneath, and this is the side view with the 2 4 axes. So the PISA predicts an aggregation of a 3-2 hexamer for rufamycin. And however, for ecomycin, we find a different cluster, which is more like a stagger, superimposing or overlapping trimer that produces different kind of an aggregate. And so we kind of use that idea to speculate as to the mechanism. We speculated that the fact that we have to go through a series of conformational changes to have that CLIPSI1 chamber in action. We'll go perhaps from A to B to C to D, and some of those are found in the crystals, possibly this one form, which is actually with the rufamycin cluster. This is the ecomycin cluster, and the two actually modify and trapped the amino terminal to kind of impede or rigidify the target. The peptides bind at the surface. It has been shown that a rufamycin site is exposed to the outside here. This is the overall model rendering of the full target, CLIPSI1. This is the N-terminal domain. This is the ATP binding domain. It's a different structure coming from the PDB. It's not our structure, complex. You can see that it's accessible to the surface. Here it is, the pocket. Here is the pocket for the rufamycin binding to modify this, which is the hexamer of the CLIPSI1, side view, 90 degrees away. And I have here a rendering of this kind of a structure. I mean, our peptide is bound to the structure of bisatylase CLIPSI1, and you can see how beautifully the whole thing is. This is the actual cluster of the 6 molecules around that ring at the top of the peppermill grinder at the top, and Claves kind of interacts with the 7 unit underneath, which is the hydraulical part. And this is kind of a pretty much, now I'm going to describe how these data are used to actually, by the chemist, to produce compounds that can be better binders and more potent compounds. Here we have here some of the typical SAR tables that medicinal chemistry produce. Here's the native rufamycin here, 10 MIC nanomolar with the epoxide and the closed ring. Actually do some variations on this. You can find that by producing variations here, from here to here, you lower the potency dramatically. So you explore this, and the chemists are doing modifications to produce better compounds based on our structures. Those are the areas that I've been touching on, R1 and R2, which are here, derivatives R1 and R2s. Here's the epoxide ring, here it is, and how we modify this. I mean, this is the chemist work. These are our structures to guide them, how to modify changes. You can see the pocket for the indole tryptophan there. And now for the ecomycin, similarly, you can see the tail here, how there's a very critical hydrogen bond between the med1 and the tail of the ecomycin, and as is shown here, when you modify that tail, as in the compounds that have no tail or they are shorter tails, these compounds are not active. So this is how this data illuminates the chemist and the drug discovery process to improve those compounds. In conclusions, just to summarize, the structures of CLIPSI NTD domain complex with rufamycin and ecomycin present unique features that should relate to the mode of action. There is 2 ecomycin molecules for one, and this could lock the CLIPSI1 NTD, etc. And there's a covalent bond. This is just a summary of what we are trying to convey to the chemists, how they can optimize and capitalize on this information to produce better compounds. I think I will close here, but I'm going to close with a small homage to Michael Rossman, not only for him, he was a towering towering figure, as you know. Molecular replacement is now present in about 2/3 of the structure of the PDB. 2/3 of the 2,000 structures of molecules in the PDB are solved by molecular replacement. At the time, nobody believed him, but as many folds have been discovered, you get the PDB entry, you get the fold, you put into molecular replacement packages, and bingo, within minutes, you have approximate phases to begin refining the structures. So a small homage, but I want to quote his kind of a vision as to why we do research, and I corrected his vision with the last item. He quoted and said, why do we do research? And said, one is the personal enjoyment of discovery. Nobody will doubt that. If you're in research, you're doing that for some pleasure, intellectual pleasure. The other, perhaps, you are lucky. If you are lucky, you can discover your things. If you are lucky, you might contribute something to humanity, human knowledge. But whether you do that or not, I would like to add the third item. That's why I corrected his vision. And I said, and to maximize our human potential. I think we have, we and you young people have a moral obligation, in my opinion, to maximize your human potential. Not just kind of, I do this job, I get the money, I go on vacation. I disagree with that. You have to strive to capitalize your human potential because you have received so much already. You have found the internet, you have found GPSs, you have found all these kind of things. Well, that didn't come out free. You have penicillin and many other things. So I impress upon you that you have the moral obligation of developing your human potential to the fullest. Thank you very much.
Thank you.
Oh,
No, it's okay. Thank you, Cele, for this inspirational talk. Let's have some discussion, time for questions from the audience, crystallographers.
Yes, of course. I hope I didn't go too fast. I wanted to cover the basic information from the target and the project and something else.
Thank you very much for your talk. Can you comment, please, a bit on structure-based drug discovery in terms of artificial intelligence?
I should point out that as a matter of fact, I published an editorial in the journal Drug Discovery today, that you are familiar probably then, in which I talk about that very same topic. And I mentioned the following concept. You go to Drug Discovery today and will find it, but I'm going to give you the summary. I start by putting this metaphor. Suppose you have a team of artificial intelligence that are going to try to solve the following problem. Classify objects, whether or not they float in water. And of course, they start with their tricks. You know, they produce, this object floats, doesn't float, color, material, size, etc., etc. And of course, they find that they can only get very, very poor models, right? You get some regression, 50, 40, 60%. There are more variables, different materials, there are different, perhaps, dimensions of the object, blah, 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 blah. They continue to do this. They create new networks and the whole work. And the point is the following. Has anyone mentioned the idea of density? Mass divided by volume? Artificial intelligence, as we know it today, cannot produce a combination of variables that is the best suited to solve those problems. I argue that point, and I emphasize that also because, as he read in my curriculum vitae, I the idea of applying what I call alternative variables for drug discovery. In particular, ligand efficiency indexes you might not be aware of, but I've been pushing on the idea of, as opposed to KIs and blah, 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 and then apply Lipinski rules later on and say, let's just get this compound more active. I said, no. Let's just define from the very beginning the efficiency of potency divided by size of the molecules, a combined variable that doesn't happen yet in artificial intelligence, or surface efficiency indices, which is the affinity divided by the polar area. And when you combine those two variables, you read the papers and you read the article that I discovered today, you will find that with those two variables as modified or alternative variables, you can guide drug discovery by purely algebraic concepts. That's read the editorial and we can comment on that. You have my email. There's many papers published on that. I've been working on this since I was at Abbott Laboratories, 2005, paper in which they define ligand efficiency indices as variables which are alternative to the conventional, which are biased on the SAR table. So you do that kind of thing, look at the editorial, you will see the concept. So I think that, yes, they could help us, they had to use the appropriate variables. And I emphasize that in any problem in technology and science, it's critical to find the correct variables. And I mentioned in passing that the motion of the atoms, of the planets, by Kepler and Newton, were characterized, defined, and studied in polar coordinates. And in this essay, I emphasize the fact that those two variables that I mentioned, if I can sketch something on them, is there a board here? I can use a board, kind of a board or something. Can I do something? Since the question came up, can I write something? Is there a kind of a shock, old-fashioned shock? Oh, perfect. That's perfect. So old-fashioned now. Thank you. So let me just you give me 2 minutes. I can define those variables and I can emphasize to you what I mean. So typically let's just kind of put only a molecule. Sorry, one variable only for affinity, right? You can also put IC50. You can put the KD, etc., etc. But the point is the following: you have this, which are the affinity variables, right, in the tables. Then you combine and say, yes, molecular weight, blah, blah, blah. So let's just put here now molecular weight as a concept of size, right? And also polar surface area as a concept of polarity, right? That's understood. So now I define variables. The simplest of all is this BEI, which is the pKi divided by molecular weight in kilodaltons. Understood? Very simple. Combination of variables. Think of density, like I mentioned. A ratio, very simple. And then you define SEI, surface efficiency index, which is the same pKi divided by molecular weight, per surface area divided by 100. Okay, just a combination of variables. Very simple ratios. Now the magic is this. If you plot those variables on a Cartesian coordinate system, which is very familiar for the drug discoveries, for the medicinal chemist. Now what happens when you do these kinds of things? You divide BEI on the y-axis by SEI by the x-axis. By algebra from high school, that is the tangent, right? The tangent. So that means that you can put any kind of complex that contains a compound that has a certain affinity with appropriate properties. You can put those compounds along a line because the ratio BEI over SEI is equal, because of the definitions, to 10 times the PSA divided by MW. And notice, this says to you that the line in that plane, the polar coordinate angle, or the compounds are along lines. So you see that this line has a certain series of compounds that contain certain PSA over MW, right? Now, where in that line depends on the affinity. So you have now separated, decoupled the chemistry on the slope of the lines with the affinity on the radial coordinates. And this, by definition, the best compounds are always on the northeast. You optimize this variable and this variable. That is the concept I'm trying to pursue in that essay, in my publications from 2005. If you use the appropriate variables, you can certainly modify and improve on the idea on how to do drug discovery, almost in algebraic terms. So I'm sorry to digress, but the question came up.
What you claim is that the artificial intelligence programs are not using this sort of...
They are not. That's what I'm trying to... Actually, the actual title of the editorial is called Artificial Intelligence and Alternative Variables in Drug Discovery, a Promising Alliance. That's the title of the editorial, and has reference to previous papers with these concepts. It's a bit more elaborate, but this is the basic key. If you don't understand, you can refer. You get my email address, it's published all over the place. But this is like I said, the editorial Drug Discovery today just came up a few months ago. I was thinking about making a right paper, long paper. I said, no, it's better to just put a punchline and tell people what to do. And that metaphor is very clear. Artificial intelligence is good for certain things, but so far, as far as I know, they have not been able to produce algorithms that will characterizing analytical expression for anything. You can classify images as landscapes, mountains, faces, whatever it is. But as far as being able to extract an analytical expression for certain things, as far as I know, they don't know how to do that yet. Yes, sorry, it took long, but I hope it was.
Thank you very much for this inspiring talk. So I wonder, as you have been working in a company for many years,
Yes.
and also in the academic
Yes,
area, so I wonder if you could comment, how can we improve our data, or how can we work in order to really make more translational research in order to, because in some cases we are dealing with specific structures, as you did in your presentation, but how to transfer this information to the companies in order to really provide a new molecule, a new antibiotic or whatever.
Well, I think I suggest that you enter in contact with them. No, try to make contacts at the personal level, at the institutional level, and give seminars and show them your methodology. Because unfortunately, I was in Barcelona for a while, as you probably know her, and I tried to do that kind of thing. But I couldn't there was not enough interest on this methodology that was very expensive to produce. Convince them that it's not very expensive, it's easy to do. And go there and give seminars, say, can we possibly connect on certain topics? What are you working on? What can I do? What are your enzymes? Trying to find or introduce postdocs that are from your laboratories into the industry, and tell them these people have been trained by us, that they know how to do these things. You can use this technology. That's my impression. I mean, I was lucky enough, it may be the dynamic in America. I worked at Abbott Laboratories for 22 years. 22 years. Then I retired from Abbott, and as a matter of fact, I was having these ideas when I was at Abbott. I couldn't develop them because I told them, let me have it 5% of 20% of my time on my own ideas. They didn't buy that. They didn't buy that. So I had to go on my own, retire from Abbott Laboratories, and then go into the UIC environment, which is a pharmacy department. It's extremely flexible and academic laboratory. But they're also applying practical problems. Tuberculosis is a very important practical problem. Very important. Go there, show them your tools, what we can do, what we cannot do, that kind of thing. That's my suggestion. I mean, we can talk at length, but that's my suggestion.
Okay, thank you very much.
Thank you very much, Tele, for this nice talk and for visiting us. I wonder how common is inhibition mechanism of peptides going through the formation of covalent bonds. Is this a peculiar system, or do you know about other systems?
The chemists don't like it very much because they create all kinds of things, but at the same time, that was a kind of idea that would not look very well. The problem with that, in this case particularly, is the epoxide ring, which is so important for this interaction, is very labile metabolically. So when you put this compound into the bloodstream of a human being, that epoxide doesn't last too long. So you cannot base a mechanism on an epoxide ring. Sometimes those hot spots, which are very active for any kind of design of interest for your molecules, they are labile metabolically. And that blocks them out. Because once they are there, in a few minutes, they are kind of disappear from the bloodstream. So that's the other side of the coin. The compounds that we have now, they don't use the epoxide. They actually use a variation because the epoxide is very labile. Opens are very quickly. And the chemists, on their credit, they do what they can. You can tell them, do this and this and this and this. They say, I just cannot do that. I cannot do that. I cannot do that. So they have to let them free. It's a combination. At Abbott Laboratories, I faced that problem many times. The fact that do this and try this, and they say, we cannot do this. We just cannot do this. We have to do what we can. This is but at the same time, some drugs do act like covalent bonds, as we know. So it's always nature is very subtle, but this helps to explain some of the subtleties at high resolution, not by cryo-EM, at high resolution.
Okay, and can you comment, what's your opinion about how can AlphaFold assist in drug discovery?
I'm sorry, I cannot.
AlphaFold. How can AlphaFold assist?
AlphaFold can help because once you prove that the molecular replacement model is good enough, you can try it. AlphaFold will help on that, hopefully. In the past, we tried to do molecular replacement models and tried to do that, but they were not good enough. They were not good. I think that if you're desperate and you have any fold, try AlphaFold. Why not? I mean, but you have the data, you have crystals, and you have the 2F4 minus Fe map to guide you. You get the approximate phases to start with, and then you refine. There's nothing wrong with AlphaFold. Nothing wrong with AlphaFold. I don't think so. I don't think so.
Okay, thank you.
But for certain things, you know, as a matter of fact, the devil is in the details. Devil is in the details.
Thank you very much for the talk. I really enjoyed listening it. I have a question regarding how accessible these drugs that you have found for MTB. I mean, you have demonstrated how they bind to the target, that they are accessible to mycobacterial tuberculosis by the initial screens.
Oh, they are. They are active.
But how well can they access the target, given that MTB infects, for instance, intracellularly macrophages? Do you have any information of how well?
Of course we do. Of course we do. Of course we do. We have compounds. We also monitor their activity in macrophages because, of course, they are latent for a long time. We have to see how penetrating they are. So the chemistry plays a role. Some compounds go into macrophages, some others don't. I just give you the glance of what we can know, and the chemists pursue the work. No question about it. We follow the macrophages and also the penetration of the macrophages, lifetime of the macrophages, etc., etc. We follow that up. It's not my field, but it's certainly look into, definitely.
Thank you.
We have compounds I cannot quote. By the way, let me just do something here. I'm sorry. Can I go one more slide? Let me see if I can. I want to emphasize this. That leads to the point. This work has been done by a very important grant from the from the NIH for this call, which is called the Center of Excellence in Translational Research. Because this grant was given to the TB Alliance, the TB Global Alliance, which is the entity which is in charge developing new medications for tuberculosis. We were part of the grant as far as structural biology, but this alliance has created many compounds are pursuing those ideas to optimize them for actually therapy and regimentations that include to actually either as supplement or as independent therapies. So this is their work. The TB Alliance, we are talking about this, you look into the web, the TB Global Alliance is a remarkable force for tuberculosis. Use those compounds to the clinic, etc., etc.
I have another question regarding the structure of those peptides, cyclic peptides.
Yes.
Especially referring to the impermeable outer membrane of MTB. So do you have any idea of, one of the challenges to cross to cross that outer membrane. So is there any characteristic properties of these peptides that make them more susceptible to cross that barrier?
Well, we do not know that yet. We are working on the formulation of ecomycin in particular. We have compounds that are good in the rufomycin scaffold, and they are penetrating and they are active. But the ecomycin is proving to be a challenge. And we are working actively in nanomolecules, nanospheres, all kinds of nanotechnology to formulate the ecomycin, because it's very potent. Ecomycin is more potent than rufomycin, but the formulation and the size is very complicated. Absolutely, that's an issue. But no, that doesn't apply that. But using these ideas for more conventional molecules, using this idea that I mentioned here, this one here on the board here, I'm sorry, underneath, ligand efficiency indices, you can actually direct the drug discovery process very effectively, in my opinion. They are not part of the common territory nowadays of drug discovery, but I think that the time has come for people to realize that you can actually direct almost algebraically the drug discovery process if you combine the variables. And it's all published. I'm sorry. So I cannot give into the details of that. I can give several talks on binding efficiency indices. But if you go to that editorial that's just published in Drug Discovery today, you can find references to previous papers, etc., etc. It's all the algebra is detailed there and applications, etc.
Here. So I have like this is out of curiosity. So you've been doing macromolecular crystallography for over 40 years now,
Yes.
let's say 40, and maybe like kind to show to the younger audience, back then, like 40, 30 years ago, how was the like workflow? Let's say what was supposed to be achieved during a 4-year PhD in crystallography?
Yes.
How was then and how is it now?
Well, at the time, unfortunately, and this happens still now, that the PhD in crystallography imply producing a target, expressing it, purifying it, and crystallizing it at the time. That was very challenging, to the point that unfortunately you only do the crystallography and the interpretation at the end. So you spend most of the time producing clones, modifying clones so they crystallize. I think that was, in my opinion, at the time it was required, but that has changed now. At the time, spending time producing the proteins, purifying them, expressing them, crystallizing them, you spend about 90% of the project, the thesis, in actually doing those steps. And then you at the end solve the structure or fail the structure, and then you have to interpret the results. So at the time, you would spend very little time in the interpretation. Now, that has changed dramatically now, because you have much better models, better methods to produce a protein, express it, crystallize it, and the technology for solving the structures is very fast now. So you can spend more time now, in my opinion, in explaining the biology and the mode of operation of those enzymes. In the past was hopeless. You spend most of the time doing the drudgery of purifying, crystallizing, blah, 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 and only a little bit of time. Now, I think that the paradigm has changed in that regard. That's my perception. Especially, like I mentioned, now you have 2/3 of the structures, 2/3 of the folds in the PDB are molecular replacement. You don't have to do MIR. Even 40 years ago, you had to do even sometimes MIR to get the thesis. Isomorphic replacement. But nowadays, you go molecular replacement, bingo, you are accepted. And that's something you could impress upon people, because it has the reputation that it will take a long time to solve a structure and refine it. Nowadays, you can impress upon them and say, we have so many proteins already in the databases that we can solve the structure very quickly. And we can help you now, immediately. I mean, when I was at our laboratories at the synchrotron, even at the beginning of the APS, you read an article that I wrote, an essay. I like to write essays, and they are under the subtitle "Notes of the Protein Crystallographer." You go into ArtaCris, you will find many essays of mine under the upper title called "Notes of the Protein Crystallography." And there are some of those. One of them talks about robots and how, with the robot mounting and the rapid technology of the APS, you can get the structure, go from the data collection at the APS day one, and within hours, you have the structure for the chemist. Here it is. Here's the structure. That's a complete change, total change, in my opinion. That didn't happen before. I mean, when I was at Abbott, employed at Abbott, it was 1985, you still have to do MIR in many cases. Replacement, isomorphic replacement with metals. That is unheard of these days. Unheard, totally unheard of. I'm sure that he can comment on that too. Any more questions, please?
All right. No more questions, comments? Okay, so let's thank Fele again for his...
It was a pleasure. It was a pleasure.
For his visit and his beautiful talk. And we would like to give a souvenir to you from the Institute as appreciation for your
This is
visit.
enough of a souvenir. Being able to be here with you guys.
So you can remember us
Of course I will remember you.
back in Chicago. Thank you.
It's very heavy.